this video will talk about sensitivity function and how to address the certain issues with regards to this function itself. And therefore, in order to do that, I'm going to address in terms of gain and phase. Alright, if you remember gain margin and phase margin, what it is? The higher the gain and the higher the phase margin, this means that it is more stable. So for example, if I will zoom into this nyquist plot, alright, the gain margin is simply the distance from here. Alright, lambda is this. 1 divided by lambda is this distance. If your distance is actually very short, this means that you are actually closer to -1, which is very dangerous. So therefore we want a higher gain margin over here. Alright, this is the meaning of it. For example, if you still don't understand, lambda is over here. If lambda is the distance between this the nyquist plot and the origin, right? If it's 0.05, 1 divided by 0.05 is equals to 200, I think. Yeah, to 20, sorry. So you have actually 20 gain margin in order to reach this. So you are actually very far away from the -1. However, if this distance, alright, is about approximately maybe 10. Now 1 divided by 10 is actually 0.1. So you are actually 0.1 from the -1. So in other words, your nyquist plot is somewhere over here right now. So you're actually closer to this. So this is the reason why we want a gain margin and phase margin to be as large as possible. Alright. For the gain margin is simply the distance from -1. We want it to be high. Now we talk about gain margin. Gain margin is, phase margin now, alright? Phase margin is simply, if you take a look in terms of -1, there's a radius of 1, alright? And we have a nyquist plot that somewhat plots like this. Okay, that crosses out of the, actually this should be symmetry lah. Okay, that crosses out over here. And this point over here, okay, theta, alright, so 1 minus 180 plus theta will give you this alpha over here. This phi, okay, this phi angle over here. This means that how much angle will you reach this -1, alright? So therefore this angle, alright, if let's say I have a lower theta angle, for example, if my nyquist plot is somewhat safer, or in other words, if somewhat is over here, alright, then the angle over here, it's kind of shorter, right? I have a lower theta and a more phi angle over here. Alright, this is the phi angle, or maybe I should with a different color. This is an angle of phi, and this whole thing is -180 degrees, right? Plus theta. So if theta getting smaller, maybe 50, I'll have a more phase. This means that I am -180 degrees from -1 point, right? So this means that I'm safer from -1. So gain and phase margin is simply that. Is the higher number it is, the safer you are. Now let's talk about sensitivity function. However, we have a problem when we're talking about this thing right here. Alright, at this point we have very huge lambda. We have a very small lambda. We have a very small lambda over here. So 1 over lambda is equals to a very huge number. We call it infinity because it's really very huge number, very small number. Alright, so our gain margin is very high, which is good. Now we talk about phase margin. Phase margin is somewhat very safe. It's really far apart. Alright, it's really far apart from the -1 region. Alright, this angle over here theta, and this is the alpha. And this alpha is actually so big of an angle, we are all safe. But the problem is that this portion over here, or this portion over here, is actually very near to -1. Alright, it's very near to this point. And this is very dangerous, and there is nothing to measure this. However, in contrary, in this case, we are actually measuring this distance right here. Alright? And measuring this distance is talking about 1 plus CP. Okay? This curve itself is this whole curve, this nyquist contour is in fact CP. Okay, later on we'll talk about it. But so 1 plus CP is simply this this distance. Alright, if you are very near to -1, this means that your so-called the sensitivity margin will go up, or sensitivity function. Okay, so in other words, if you are really near to this -1, for example, maybe like 0.005, sorry. So I'll have 1 over 1.05. What I have will be 0.95. Okay, if my distance, right, if my nyquist plot is somewhere over here, it's somewhere larger, alright, this distance is perhaps 10. Alright, this means that 1 plus Cp now is equals to 10. So 1 over 10 is equals to 1 over 1 plus 10, because what am I talking? Sorry, my fault. 1 plus Cp is simply the distance, and then I don't know what the hell am I doing over here. So for example, again, for this distance over here, this is 1 plus Cp, which is 0.05, right? So 1 divided by 0.05 is actually a very big number, right? Indeed. Now, if I have a new nyquist plot that is somewhat over here right now, instead of this one, okay? Then the distance, maybe I change color, the distance over here is larger. So 1 plus Cp over here, perhaps this distance is 10. And therefore 1 divided by 10 is equals to 0.1. And what does this implies? If you're nearer to -1, this means you're more sensitive to system variations. System variations means that any disturbance that will cause you to go to unstable or things like that. So the higher number it is somewhat the more dangerous it is, I would say. Alright? But as I say, the higher number it is, the more unstable it is. So it's somewhat contrary or inverse related to gain and phase margin. This one is the higher, and the higher the gain on the phase is good. For this case, the higher the sensitivity function, this is bad because it's not robust. So later on we'll talk about what is robust and all things like that, but we just want to introduce with the concept of sensitivity function. Alright, so the larger the number it is, the more you are nearer to -1. That is the meaning. And the sensitivity function in this case is what we call the vector margin. It's just the distance from -1. That's all it is. Therefore, in the next video, we'll actually share with you how do I derive this equation over here. Okay, and I'll see you there.